Hi, this is Randy with Sophos Tutor, and I just want to say a quick thank you for clicking on this video. Also, if you haven't already, please click subscribe to Sophos Tutor, as it really helps out with the channel. Thanks.
Okay, so for today we are going to answer this question involving parametrics. So we're starting with this curve. Right? So this curve says x plus 3 squared over 1 plus y minus 4 squared over 16 equals 1. We need to complete the following. The first question is asking us is to write a pair of parametric equations for the curve. Right. So how do we do that? Well, we want to start with the equation that I think most resembles this format, this time using parametrics. And the parametric variable we're referring to is t. All right. So this is a parametric variable. Okay. We're going to start with the parametric variable, and we're going to use what's called the Pythagorean identity. All right. The Pythagorean identity says that the cosine squared of t plus the sine squared of t is equal to 1. All right. Why is this equation useful? Well, if you compare it to this equation, which by the way is the equation of an ellipse, you see that the formatting is actually very similar in that we have an entity being squared, right, plus an entity being squared. That's equal to 1. So if we follow this format, we can see that the cosine of t, we can set this equal to x plus 3 over 1, right? Now, for this side, we do want to adjust things a bit, okay? Because notice that the 16 is not squared. So if I wanted to rewrite this, y minus 4 squared over 16, but I really want to rewrite it such that I have a whole entity squared, well, this would be equivalent to y minus 4 over 4 squared, right? Remembering that if we square a fraction, that square is going to be distributed to the numerator as well as the denominator. So we can say, therefore, that sine of t can equal what's inside of the square, which is y minus 4 over 4. I will also add here that traditionally, we set the x term equal to the cosine and the y term with the sine. Theoretically, you could switch them over, but some weird stuff tends to happen with it. I won't go deeper into that. Maybe I'll do a video regarding why we set the cosine of t typically with the x variable and why sine of t is associated with the y variable. But for now, just trust me that this is the convention. And so to get the pair of parametric equations, we simply just isolate the x and isolate the y. So this one is sort of taken care of already. All I need to do on both sides is to subtract by 3. All right. And so we end up getting x is equal to negative 3 plus the cosine of t. I'm just going to write it this way, just so that we don't confuse the t and we're not subtracting 3 from t. For the y equation, we're going to need to multiply by 4 on both sides first. Okay. Then from here, we're going to need to add 4 to both sides. Okay. So here we're going to get y is equal to 4 plus 4 times the sine of t. And here are our set of parametric equations. So this is going to take care of part A. Now for part B, question's asking is how could you graph just the right side of this curve? Okay. We first have to acknowledge here, it's not mentioned in this problem, but typically when we deal with parametrics, we limit the value of t from 0 to 2 pi. T is in the form of radians, right? And we know that 2 pi radians represents an entire circle. So this is typically the life cycle of t, starting at 0, ending at 2 pi. Now, if we used those terms, this limitation here, this is going to create the ellipse if we followed these parametric equations together, okay? So let's just draw this parametric equation first, okay? We can draw this based off of the original equation, right? So we know that the center of this ellipse is going to make both fractions equal 0. So I know that my x value is going to be -3, right? Because I plug in -3 here, it'll make this top part equal 0. And I know my y value is going to be 4. So -3, 4 is going to be our center. Let's go ahead and graph that here. So -3, 4, so 1, 2, 3, up 4, so it's going to approximately be up here. Let's say this is -3, 4. Okay. Now, these values here represent the square of what we call the semi-axis. The semi-axis is just another way of saying halfway across, right? Kind of similar to a radius, except that unlike a radius in a circle, where all the distances from the center are all equal to each other, right? So for example, if I have a radius of a circle, the radius is the same regardless of the direction I go in. In an ellipse, obviously this distance from the center to the edge is changing. So this 1 represents that at the farthest point, to the left and to the right of this center, we're going to travel a distance of 1. So we're going to have a point right over here, which is -4, 4, and another point over here, which is -2, 4. And this is the farthest that this ellipse will go left to right. Now in the y direction, we see that the number in the denominator is 16. Remember, this is the square of the semi-axis. So that means the semi-axis in the y direction is actually the square root of 16. Square root of 16 is 4. So we need to actually travel a distance of 4 going both up and down. So if I travel 4 units down, I'm going to hit -3, 0. And if I go 4 units up, I'll hit -3, 8. And so this parametric equation is going to follow the path of this ellipse here. All right. Okay. Now, what parametrics describes beyond what the x and y equation says here is the path of the particle and where a particle is on that path in a given time, right? Without the parametrics here, all we see is this path, but we don't know where the particle is on this path, and we don't know what time the particle is at any given moment, right? But if we include parametrics, if we start at t equals 0, we know where this particle is going to start. So if I plug in 0 into this x function, so we're going to say this is x, and put a parentheses 0, indicating we're placing the t with 0. We're going to get -3 plus the cosine of 0. That's going to equal -3 plus 1, and that's going to equal -2. So the x value is going to start where -2 is. If we plug in t equals 0 for the y equation here, so y of 0, we're going to get 4 plus 4 sine of 0, which is equal to 4 plus, well, the sine of 0 is equal to 0. 4 times 0 is 0, so it's going to equal 4. So the starting point of the particle will be at -2, 4. So right now, the starting point is at the rightmost point of this ellipse. Now, what happens as t increases? Well, if we look at the y value, we know that when sine increases from the angle being 0, we know that this value here, this 0 here, is going to go up. We recall this, that when we graph sine, we know that the curve initially goes up. So we know that as t increases from 0, we know that this value sine of 0 is going to increase, which means that this y value is going to increase. What that tells us is that when we have a starting point here at negative 2, 4, it means that this particle is going to move upwards. So we can say that this particle, starting at negative 2, 4, is going to move in a counterclockwise direction around this ellipse, like so, and end at negative 2, 4. Okay. Now I'm gonna, you can tell I'm already running out of quite a bit of room. So I'm gonna go ahead and erase this top half here. Now going back to this question on B, how could we graph just the right side of this curve? So the right side of this curve consists of this half right here. Okay, how do we cut it off? Well, there are two aspects that we need to consider. First, how do we make sure that only half of the curve is going to be followed? Well, remember our restriction goes from 0 to 2 pi. If we could, we would like to cut this t off so that instead of going from 0 to 2 pi, we go from 0 to pi. But with parametrics, we kind of don't want to directly change this range because we like the idea of this t traveling in a full circle. So we're not going to change this domain of t, but what we can change is the angle that's being put in these trig functions, right? So the easy way to do that first is to simply replace this t with t divided by 2. Okay, x equals a negative 3 plus the cosine of t over 2. And for y, this is going to equal 4 plus 4 times the sine of t over 2. Okay? So notice that by dividing t by 2, we force this particle to essentially move slower. So that instead of the ending point being where we started, the ending point is simply halfway across the ellipse, right? So these parametric equations would graph the top half of our ellipse. Now that's not exactly what we're looking for, but it gets us closer to what we're looking for. Now what we really want is, instead of the starting point being in the middle of that curve, we want the starting point to be actually at the bottom of that curve. Right? So how do we force this t to start down here? Well, we can take away some of the radians here, because if the radians at 0 typically start here, well, when we set t equals 0, we actually want to move those radians back. Well, how far are we going to move that back? Well, we're moving it back a quarter of the cycle, right? And how much is a quarter of a cycle in terms of 2 pi? Well, that quarter of a cycle is about pi over 2, or 1/4 of 2 pi. So we can change these equations so that we can offset the starting point of the angle that we're taking. So in this case, we're going to keep the t over 2 part, but we can also subtract pi over 2. Okay? We'll do that also with sine, t over 2 minus pi over 2, right? So just to review, if we plug in now t equals 0, instead of taking the cosine of 0, we're now going to take the cosine of negative pi over 2. Let's test that out. If we took the cosine of negative pi over 2, again, we're plugging in t equals 0 now. Well, the cosine of negative pi over 2 is 0. Right? If you don't believe me, go ahead and check in your calculator. So our starting point is going to be negative 3. If we take the sine of negative 2, or sorry, if we take the sine of negative pi over 2, well, the sine of negative pi over 2 is negative 1. Again, you can check that on your calculators. So we'll get 4 minus 4, which is equal to 0. So our new starting point is negative 3, 0. Well, where's negative 3, 0 on this ellipse? Oh, it's on the bottom. So we've successfully shifted our starting point from the right side most part of this ellipse to the bottom of this ellipse. And we have adjusted the angle in such a way that we're going to stop at the halfway point of this ellipse. So these right here are the new collective parametric equations for the right half of this ellipse. Okay. Now moving on to part C, right? I'm going to have to erase this again. So for part C, how could we just graph the bottom half of the curve? Let me draw the ellipse up here. Over here, we are centered at negative 3, 4, which is approximately up here. And we got an ellipse that looks like this. And our typical starting point was right here, which was at negative 2, 4. This is negative 3, 0. And we want the bottom half of the curve. Remember that the original parametric equation we had was negative 3, the cosine of t, and y was equal to 4 plus 4 sine of t. Okay, so we're going to follow those two steps again. First thing is, let's make sure that only half of this ellipse is graphed. Well, we're going to follow the same technique that we did before. We're going to go ahead and replace t with t over 2. Right? Remember, this is what will allow us to only graph the top half of our ellipse. Now, what we need to do is we need to shift the starting point, because we know that we are traveling counterclockwise. We want to shift the starting point to start on this side of the ellipse and then move this way. Right? So what is going to be the offset here? Well, we want to shift this halfway across our circular shape. Since our domain is 2 pi, that means we need to travel half of that 2 pi. So what we're going to do is we're going to add pi. Let me move this here, erase that. We're going to add pi to our parametrics. Right? So now instead of the top half, this is going to be our bottom half. Okay? There we go. Right? And to test this, we can actually go into a graphing calculator with Desmos, and we'll take a look at what these parametrics will actually look like. So we now have Desmos pulled up. In order to graph parametric equations into Desmos, we need to write the system of equations as an ordered pair. So we're going to follow the ordered pair conventions of the x-coordinate and the y-coordinate, but instead of putting in typical numbers that we'd normally put as the x and the y, we're going to put in those expressions. We're going to put in those parametric expressions into those slots. So the x value we said was -3 plus the cosine of t. And for the y value, we said it was 4 plus 4 sine of t. Okay. Now, the reason why this looks weird is because we set our limits to 0 and 1. But here we want to set our limits from 0 to 2 pi. And notice we have our full circle. Okay. Now, if I replace these t's with t over 2, like that, and the t divided by 2, like this, and you notice that we have successfully cut this ellipse in half. Now, we also said that in order to create offsets, we can subtract and add to this value to change the starting point. We said that in order to do the right half of this ellipse, we were supposed to subtract pi over 2. So if I subtract pi over 2 from our cosine, and if we subtract pi over 2, right side, notice we have the right side of this ellipse. We also said that if we wanted the bottom of this ellipse, instead of subtracting pi over 2, we could add pi. So we add pi here. See, it's interesting actually, like, because as the graph changes, it's interesting that this would be a straight line. I think there's something to investigate there, right? We add pi here and we have the bottom half as well. Now, it happens to be coincidental that we can also subtract pi as well, because these radians work in a cycle. Notice that we don't have to push forward the starting point forward by 1/2 of a cycle. We can also push the starting point back 1/2 of a cycle, and notice that we end up having the exact same starting point. So that is our lesson on parametrics. So hopefully you learned a little bit about how you can set up your equations using the Pythagorean identity, cosine squared of t plus sine squared of t is equal to 1. And we've also learned how we can manipulate that t in order to graph only parts of that ellipse, by dividing that t and then creating offsets to both add and subtract from that angle.
Thank you so much for watching. Now, if you liked what you saw, please click the thumbs up button below. Also, if you want to watch more of my videos, or you want to catch me on an office hours live stream, please click subscribe to Sophos Tutor.